Now that we've decided what the characteristics of a so-called good-looking quadratic graph are, let's go ahead and think about one of many strategies for graphing a quadratic given its equation. Um, so just as a quick reminder, if I have the standard form of a quadratic here and I let these sliders play, you can see that the quadratic is changing the way it looks, but a couple of things stay true no matter what. This is a little bit dizzying watching this parabola do all the things it's doing, but it's always going to have a vertex and an axis of symmetry that divides the parabola into two mirror images. It will always be continuous. It will have arrows at the ends and be connected with a smooth curve. It's never a V shape. Parabolas always have intercepts. They always have a y-intercept. I mean, look at this particular one. Notice that it's always going through the y-axis. Sometimes they have one x-intercept, sometimes they have no x-intercepts, sometimes they have two x-intercepts, and they are always symmetric. What you see on one side of the parabola is happening on the other side of the parabola. So before we kind of get totally dizzy from this experience, all these actually just get turned off. And we go kind of low-tech now and look at my document camera. So I've kind of listed for you at the top there all those characteristics that I spoke about out loud. So this particular approach to graphing is a three-step process. Question one is you simply ask, does the parabola open up or down based on the equation that's given? And let me actually get right into that. So if we go back to Desmos and remember what the parent graph looks like, notice that this leading coefficient here, it looks like there's no number in front of the x squared, right? But there's actually a 1 there. It's an implied 1. Whenever this leading coefficient, whenever this a value is 1, then what's going to happen is the parabola is going to open up. And that's not something you have to memorize, because if you think about it, whenever I plug a value in for x, it gets squared, and this will determine the sign of that outcome. So right now, all of these outcomes are positive. And what's controlling the nature of that relationship is the fact that the value in front of x squared is positive. Not surprisingly, if I were to make this value in front of x negative, look what happens. The whole parabola now faces down. So if you want to know whether your parabola opens up or down, you simply look at the leading coefficient. In my case, I've got this function here, f of x equals negative 2x squared minus 4x plus 2. None of these terms, not the linear term, not the constant term, they don't concern me in answering this question. What concerns me is this negative 2. So because this leading coefficient is negative, this parabola will open down. So the answer to question one is that my parabola opens down. I'm just going to sketch a parabola opening down. And in this case, because the leading coefficient, and this gives you a chance to see my handwriting, is negative. Another way to think of it is the a value is negative. So already we have a sense of what the parabola looks like. It is a broad sense, but nonetheless it's some sense of what's going on. Question two is, where is the axis of symmetry, which will reveal the vertex to us? So, I wish there was a way I could figure out the axis of symmetry, and there is. There is a formula whose origins right now might seem murky to you, but will become clear in the next few days. But the formula goes as follows. X is equal to negative b over 2a. And if you think about this equation in its standard form, f of x equals ax squared plus bx plus c, that's what these letters are referring to. A in this case is negative 2, b is negative 4, and c is 2. I need the b value and I need the a value. And I'll write this again. It's actually negative b over 2a. So writing it vertically might help you see it a little bit better. So I want the opposite of whatever b is. Right now b is negative 4, so the opposite of a negative 4 is a positive 4. And then I want twice whatever the a value is. And the a value is negative 2. 2 times negative 2 is negative 4, and we end up with a negative 1. So the formula was x equals this business here. So I'm going to rewrite it as x equals negative 1. You might wonder, what is that? This is the equation for the axis of symmetry. Axis of symmetry. That vertical line which will divide my parabola in half. So if I do a quick sketch again here, I know that the parabola opens down, and now I know that there's this imaginary vertical line passing right through it, where at x equals -1, and on that line, x is always equal to -1 as y is changing, but it will split my parabola into two halves, not equal halves, but mirror images. So I've answered the first two questions. I know that my parabola opens down. I know, thanks to this little formula here, x equals -b over 2a, that the equation for the axis of symmetry is x equals -1. And now I want to exploit the graph's symmetry in a table. And you might wonder, well, what does that mean exactly? Well, let me reveal that to you. And before I do, in part 2 it says, where is the axis of symmetry which reveals the vertex? And you're like, well, how does it reveal the vertex? Well, the axis of symmetry always passes through the vertex. So if I take this function and I give it that input of -1, that's the place where my axis of symmetry lives. I want to know what the function value is when x is -1. So I'm going to go ahead and evaluate this. So I'm just replacing x with -1 wherever I see it. This turns into a +1, -2 plus 4 plus 2. And here I think ultimately I'm looking at 2 plus 2 is 4. So when the input is -1, the output is 4. That means that the vertex of this parabola, the place where it changes direction, is at -1, 4. We've got a whole lot of information, all of which we extracted from this one equation here. We know that it opens down this parabola. We know that its axis of symmetry is at x equals -1. We know that when we plug in that -1 into the function, because that axis of symmetry passes through the vertex, we get an ordered pair of -1, 4. That's where my vertex is. So now I'm on step 3, where I can exploit, make use of, take advantage of the graph's symmetry. And what I'm going to do is something kind of unconventional. Instead of starting the graph, or the table I should say, up here, I'm going to kind of go to its approximate center and put in the ordered pair -1, 4, because that's the vertex of the graph. And if it splits the graph in half, I want to know what's going on either side of the graph. Now, to save you some of the boredom of watching me plug in values, let's say I choose 0 as an input. Remember, we get to choose whatever inputs we want. I won't write out all this work, but what you'd really be doing is taking this 0 back to this function, and everywhere there's an x, you're replacing it with 0. And when you do that, this term turns into 0, so does this, and you're left with the number 2. Now, I have not exploited the symmetry yet. I'll show you what I mean by that in just a moment. Let's say I choose to plug in the number 1. My x values are getting bigger and bigger. If I take this 1 and plug it into this function, again, replacing all the x's with 1s, you'll find that your output ultimately will be -4. Now, if I graph just these 3 ordered pairs, you're going to have kind of an asymmetrical graph. What you can do, however, is think to yourself, wait a minute, I know that my parabola is symmetric, so if I am one space away here, from -1 to 0 is one space away, how about I move in this direction one space and land at -2? I should be getting the same output as I was on this other side. So one space away from the vertex gave me an output of 2. I should also be getting an output of 2 here. When I moved an additional space away, I got an output of -4. Well, an additional space away here is -3. And so for -3, I should also be getting -4. What I have done is exploit the symmetry. I have decided that what is happening on this side with respect to outputs is happening on this side as well. So with this table of data, I might be able to get a good graph going. My x values go from -3 to 1, and my y values from -4 up to 4. So I'm kind of sketching this by hand. Bear with me. Just making some decisions on the fly about my axes. And they could have been prettier, but I'm trying to perform here under pressure with the camera and so forth, and it takes some getting used to. So here we go. Let's do -1, -2, -3, and then a 1 and a 2 in that direction, and that's more than enough for the values that I have. And then I'll do a 1, 2, 3, and a 4 in this direction, negative 1, negative 2, negative 3, and negative 4 in this direction. And now it's a matter of finding this stuff. And I like to start with the vertex. So the vertex is at negative 1, 1 comma negative 4, whoops, 1 comma negative 4, which is down. I'm questioning myself, and I shouldn't. Negative 1, 4 was correct. That's the vertex. And then I've got another point at 0, 2. And then I've got a point at 1 comma negative 4. And now on this other side, negative 2 comma 2. And then negative 3 comma negative 4. So have a look at this. I always like to start with kind of a dashed line to give myself some confidence. In this direction here, we've got ourselves a pretty good looking graph of a parabola. It's for the most part smooth. Clearly there is a vertex here at the point negative 1 comma 4. The axis of symmetry, you don't have to draw it in, but if you want to, you can with a dashed line, is at x equals negative 1. And it has all of the characteristics that we said make for a good parabola, make for a good quadratic graph.